This lesson is on nonlinear inequalities. This is section 2.6 from your book. In the past, you should have become familiar with linear inequalities. Those look something like f of x is less than 2x plus 3, for example. So you have some linear equation and you have some inequality sign, right? Less than, greater than, less than or equal to, greater than or equal to. And we're analyzing, okay, where is that true? Where does my f of x, where is that less than 2x plus 3, for example? So you'd graph 2x plus 3, that looks something like this, and it's dotted because it's just a less than, so we know we're not actually going to touch that point. And we analyze a point, for example, 0, 0, okay. Is 0 less than 3? Yes, it is. That means the point 0, 0 is included. We shade that area. Those are the sorts of answers we had to linear inequalities. So for a polynomial inequality, we're given some f of x, and again, we're analyzing, that's going to be when we have less than, greater than, less than or equal to, or greater than or equal to. And we have f of x, one of those signs compared to 0. So we are analyzing when our f of x is less than or greater than 0, or less than or equal to, or greater than or equal to 0. That means our f of x is either going to be positive or negative, right? That's how we define less than 0 or greater than 0. Hopefully all of you know that. So we can evaluate polynomial inequalities by examining what happens between the zeros. So a very special thing happens often when you have a zero of a polynomial is that you cross over into a positive or a negative area, right? So when we're talking about f of x is less than 0, we would say, where is our polynomial negative? Where is our f of x negative? Where are we below the x-axis? If it was greater than 0, it would be where is it above the x-axis? So let's look at the graph we have provided here. So we have something starting for negative x, we're at like positive infinity. Then it looks at like negative 4, we have a 0, and we're in the negative area. Then at negative 2, we hit a 0 again. We go back to positive. Looks like at positive 2, we have another 0, so we're switching again. Then at 5, we bounce off. So we're still negative for both of those, but we have a 0. That's important because we can't always equal 0. If we had just a less than sign, then that would be a different interval. So let's look at what happens. What intervals do we actually have? One is f of x less than 0. F of x is less than 0 for negative 4, negative 2. So from negative 4 to negative 2, our f of x is less than 0. And from 2 to 5, and from 5 to infinity. So when we write this in interval notation, you'll notice that we have parentheses on that negative 4, negative 2, the 2, the 5, the infinity. We have parentheses because this just says less than 0. So it means when we actually hit 0, that's not part of our solution. Compared to when we have less than or equal to 0, that interval becomes bracket negative 4, negative 2, in union with bracket 2 to infinity, and then we have a parentheses, obviously, because we can't get to infinity. We can't actually touch it. So what we can also do is make a sign chart in order to help us remember what has happened. You know, instead of writing all of that information to the right that we have, we make a sign chart like this one below. So we put our zeros on this sign chart, negative 4, negative 2, 2, and 5, for example. And we analyze where is our f of x positive. Well, our f of x is positive from negative infinity to negative 4, right here. And then at negative 4, it switches. Now we are at negative all the way until we get to negative 2. Then we're back to positive. So we have a positive here. Then we have another negative. And at 5, we still have a negative. What does that tell you about 5? Well, 5 must have an even multiplicity of whatever of that 0. So the 0, 5 must have an even multiplicity, versus all the other zeros which have an odd multiplicity. So maybe at 4 you have x plus 4, and you just have it to the 1. You only have it one time, or you could have it 3 times, because anytime we have an odd multiplicity, we are going to pass through the x-axis. That's the rule for a multiplicity of zeros. Let's do an example. So solve 3x cubed minus 4x squared minus 13x minus 6 is less than or equal to 0. So we can use the techniques from the previous section in order to find that f of x has zeros at negative 1, negative 2/3, and 3. So what were those techniques? We looked at the constant and the factors of that constant. We divided that by the factors of the leading coefficient. That gave us a bunch of options for what our real zeros, real rational zeros could be. Then we graphed it and analyzed which of those made sense. We can plug that into synthetic division in order to evaluate our remainder and make sure we get a 0 as our remainder. And that'll prove that our f of x is equal to 0 at whatever those zeros are. So for our zeros for this problem, we have negative 1, negative 2/3, and 3. So the first thing we're going to do is to write our sign chart for these zeros. So I put negative 1, negative 2/3, and 3 on that sign chart. The second thing we can do is determine the end behavior. We know how to find end behavior given a polynomial, right? First, in order to figure out what the right end is doing, we evaluate whether or not a is positive or negative. Well, a is 3, which is a positive 3, which means that our right end behavior, so that's from our last 0 all the way to infinity, that's going to be positive. We're going up to positive infinity, so it has to be positive. Our left end behavior is defined by whether or not n is even or odd. So at this location, we have 3x cubed. Cubed means odd. So what happens when n is odd? It says the opposite of the right end. So we know that our left end behavior is going to be negative. We're going all the way down to negative infinity. So we analyze the multiplicity of the zeros. That's our next step. So for this problem, our zeros are all of multiplicity 1, which means they're all odd. What does that mean? It means that at each of those zeros, we are passing through the x-axis. If we pass through the x-axis at a 0, we're changing our sign. So you might change from negative to positive, or if you're passing through the x-axis, you could change from positive to negative. But you're always going to change your sign. Your y, your f of x, is going to either be positive to negative or negative to positive. So if we know that, we can then start filling in the rest of this sign chart. We know that we are going from negative when we are from negative infinity to negative 1. And then at negative 1, we have to switch signs, so this becomes a positive. At negative 2/3, we also switch signs because we are also passing through that x-axis. That becomes negative. At 3, we switch signs again, which makes sense because we already had a positive from 3 to infinity. So therefore, the solution of 3x cubed minus 4x squared minus 13x minus 6 less than or equal to 0 are where our zeros, or the intervals, are where our f of x is negative or equal to 0. So where is that true? Oh, sorry, I'd erase this. Negative, positive, negative, positive. So that happens between negative infinity and negative 1. We can't touch negative infinity. It can be equal to 0, so we can touch that negative 1. And then in union with, the other place where we have a negative interval is from negative 2/3 to 3. And we can touch both those values too. So that's your answer. That's what it's going to look like. The next section is rational inequalities. We talked about rational functions in the last section where we had, some function a of x over some function b of x. We have fractions essentially. So rational inequalities can change signs. We can change from positive to negative. We can cross that x-axis or change our value of our function, not only at zeros, as we saw for polynomial inequalities, but also at points of discontinuity. So we found something very important when we were doing rational inequalities. These were asymptotes. So an asymptote is an infinite discontinuity. So at any of those, you also have the ability to change signs. So let's do an example. Solve 4 over x minus 6 plus 2 over x plus 1 greater than 0. So first, the very first step is to simplify the rational function by multiplying by the least common denominator. So in this case, we're going to multiply all our terms by x minus 6 times x plus 1. We end up with this equation, which is 4x plus 4 plus 2x minus 12, and we can simplify that, all over x minus 6 times x plus 1 is greater than 0, and we can simplify that numerator to just 6x minus 8. So if we're trying to analyze where we are going to have either zeros or points of discontinuity for this equation that we're left with, well, we're going to have a 0 whenever the numerator equals 0. That happens at 4/3. So that's a very important point to remember. Where are we going to have any undefined points? Well, that happens when our denominator equals 0. So that happens at -1 from that x plus 1 and +6 from that x minus 6. So the next step is to make a sign chart for these values and then test the values that fall in between them. So we have -1, 4/3, and 6 on this sign chart. And what we're going to do is we're going to plug in something that is less than -1, for example, and see what we get. And we're going to get a negative over a negative times a negative. Well, we can figure out what that is. That just simplifies to a negative. The next step is to plug in a value between -1 and +4/3. So you could plug in 0, for example, and you're going to get a negative over a negative times a positive. So those negatives are going to cancel out in this situation, and we're going to just be left with a positive here. On the interval from 4/3 to 6, again, you plug in some number in between those. You could plug in 2 or 3 or something like that, and you're going to get positive over a negative times a positive. Well, we have an odd number of negatives, right? So we know that that means we're going to end up with a negative. The last one we end up with positive over positive times positive, which means we have a positive. So this is what your sign chart looks like now. So the original question was find the solution of where f of x is greater than 0. So where is f of x greater than 0? Looking at our sign chart, that happens between -1 and 4/3. And this time we're just doing greater than. We don't have a greater than or equal to, so it can't equal 0. So we need to do the parentheses on this one. It also happens from 6 all the way to infinity. And again, it's just parentheses because it is greater than, not greater than or equal to. And if we look at our graph, if we graph this, that makes sense, right? From -1 to 4/3, it looks like we are in the positive y, right? This whole area up here. Anything that falls in this area up here is what we care about. That happens here, and it happens again here, between 6 and infinity. So that makes sense. Our answer is right. So that's how you solve rational inequalities and polynomial inequalities.